Okay, I will share my screen. Okay, thank you to all the attendees for joining this virtual edition about the JMAG and PSIM user conference. So today we will present you the topic about electric motor and electrical axle design by simulation and by using Particleworks software. So this presentation will be done by Michele Mirelli. So Michele Mirelli is is a project manager which coming from EnginSoft company in Italia. So it is a proposed seller manager for Particleworks in Europe, a joint venture between EnginSoft Italia and Promotech Software. Promotech, it is the developer of Particleworks software. So Michele joined EnginSoft after the bachelor degrees in Italia and a master degree obtained in Groningen in Netherlands. So he have a good technical expertise span on electric motor cooling, piston cooling, and so on. So he made a lot of study, such as the non-Newton fluid system. So he's also organized several training on Particleworks, and it also support different customer in different application industrial area. So Michele, look, you can start. I will put you presentator.
Okay. Can you hear me?
Yes, now you have.
Okay.
So you can share your screen. Yeah.
Can you hear me?
Yes, I can hear you.
Okay, perfect. So I will share the screen. If you can confirm that you see everything, we can start.
Yes. Yeah.
Okay. So good morning, everyone, and thank you, Didier, for your introduction. I'm Michele Mirelli, as said, and I'm part of the team that represent Particleworks Europe. So I'm a pre-post sale manager for this company, and together with my the team leader Massimo Galbiati. So here you can see the our emails if you want to get in touch with us. So today, as said in the title, we will discuss about the use of simulation, of CFD simulation, so fluidodynamic simulation, for e-motors and e-axle design improvement. We will see why we need simulation to tackle the new challenges that are due to the transition that we need to have in the next years, the mobility transition. So the agenda is shown here. So I will basically cover all the steps of simulating an e-powertrain. More and more we are seeing the combination of an e-motor with the transmission gearbox coupled together. So really the software can handle this coupling very well because it's very suitable for both of the simulations, both for the cooling effect in the e-motor and also the lubrication in the gearbox. So the agenda for today is going to be, after a small introduction on the company, the motivations again for the development of new e-motors and e-powertrains. Then I will go through all the Emotor's design steps and simulation steps to improve the design, and we will see what you can extract with the software in terms of informations. And at the end, we will also cover the transmission simulation, and we will see also here what are the outputs usually obtained, and also some validation in terms of simulation versus experimental results. So Particleworks Europe is the master reseller and distributor of the moving particle simulation software known as Particleworks. So this method, the CFD method, is based on the MPS methodology, moving particle simulation. It's a meshless CFD tool developed in Japan. And as Particleworks Europe deals with the distribution and the also support all around Europe for the use of this software. We are the competence center, and we collected in various years of activity specific know-how on the methodology and how to apply it to industrial situations. We support, again, high quality, in a high quality way. We support our customers, but also our distributors. There are several distributors all around Europe, and Powersys is responsible for distributing the software in France. But as you can see, we are also dislocated in Germany, UK, East of Europe, and also Turkey, as well as Spain. So what we offer is not just the simulation software that we will use and we will discuss about, but we also do consultancy services, and we also provide training and know-how transfer. Let's just see what is this methodology, and let's have a clearer view about some details of the moving particle simulations methodology. As I mentioned, is a meshless approach. This means that as compared to the conventional method, we don't need to prepare the geometry, to clean the geometry, and to mesh the fluid volume before starting the simulation, but we can start directly on the condition settings of our CFD simulation. The approach, the moving particle simulation approach, is a Lagrangian, intrinsically Lagrangian approach. So basically, the computational nodes are the particles representing small fluid volumes. After that, we can run the simulation thanks to the algorithm behind Particleworks that are easily parallelizable. We can run the simulation on GPUs, so graphic cards. And this allows for a faster, in general, simulation than on running on CPUs. So overall, we can see that when we have oil splashing phenomena or oil jets, oil spraying phenomena, in all of these cases, we can really reduce the simulation times by a factor of 2 to 10. So we make feasible the study of systems. We will see some example in the coming slides. We make feasible the study of this kind of system that were not previously investigated with a conventional CFD tool. So here is an overview of the most important application. Of course, traditionally, we have gearboxes, lubrication analysis, and also sump analysis. We will cover in detail this case. So we have a lot of rotating elements, and of course, meshing this kind of system is very difficult. But with Particleworks is easy to set up this simulation. Then we have, of course, Emotor cooling with the direct jets coming from the rotor, as in this case. We have bearing lubrication, also with non-Newtonian fluids. We have piston cooling with jets directly impinging on the piston. another visualization of a gearbox, lubrication or splashing. And also we have wading phenomena as well. So external aerodynamics and the interaction between vehicles and water, like in this case. So to investigate if we have water intakes in undesired areas. So what are the motivation and requirements of the development of e-motors? As we know, the sales of electric vehicles is really reaching a tipping point and let's say a very high growth. As we can see in the last 2 years, we significantly increased in sales of electric vehicles, especially at the end of 2020 and during this year, as reported by this graph. So it's important with this increasingly growing global fleets of vehicles to provide now very good e-motors for the automotive industry. At the same time, as we can see, we have the roadmap report from Advanced Propulsion Center UK that highlights what will be the requirements in terms of costs and power densities for e-motors in the coming decade. And already you can see that starting from 2.5 kilowatt per kilo in 2017, we will need basically an improvement, a strong improvement of a factor of approximately 3 for 2025, while the cost needs to reduce significantly. So in this framework, we really need simulation to improve the design and get the e-motor design first time right. So let's see what are the so as I mentioned, the power densities are increasing, and because of that, more and more we needed to consider different type of cooling solutions, like the oil jet direct cooling solution. So the idea is that instead of having a water jacket around the e-motor, or instead of using air for e-motor cooling, we need direct jets, oil jets in the most critical areas. And at the same time, we see that in the e-powertrain system, we have coupled axles in which basically the oil-cooled e-motor is transferred. So basically between the axle and the e-motor, we have transfer of oil with different solutions. And we have a closed circuit dealing with both cooling and lubrication. So let's start with the e-motor analysis and simulation. So this is overall what we can provide, of course, in collaboration with software like JMAG. The workflow really starts from scratch, really starts from the preliminary e-motor design, satisfying the requirements provided by the customer. So first thing first, we need, of course, to do the 3D electromagnetic analysis to extract the power losses, and also, the electromagnetic analysis of the e-motor in general to understand what properties we need to include. And then we can move in parallel, and once the model is transferred to the CFD system, we can analyze the oil cooling simulation and strategies. So here is where Particleworks enters the simulation workflow, and basically from the e-motor geometry, we will simulate a different aspect of that e-motor, and at the end we transfer the HTC maps for the thermal analysis done in JMAG at the end. So let's see what are the outputs usually, or the type of simulation that we can analyze with Particleworks. We can optimize the flow rate distribution in the shaft. So the first part is usually to balance to balance the flow rates in the different areas of the injection circuit. In this case, for instance, a rotating circuit was introduced in the shaft and the rotor, and we needed to understand what was the distribution of flow for the different RPM condition. Then what we can do is also to include the air effect. So inside Particleworks, we can simulate air in different ways. One possible solution is to simulate air before simulating oil. So in this way, we can split the particle size, so the mesh size, between the air and the fluid component. And in general, after simulating air, we transfer this information as an air field to the fluid-only, oil-only simulation, and we can extract and visualize the distribution of oil in the winding area and in the housing. After that, we transfer actually, and we map inside Particleworks the HTC on the surfaces that we are interested on. So for instance, the windings, the stator, the rotor, and so on. And we transfer these maps to an FEA solver to then achieve and obtain the temperature distribution. So actually for this step, we could either transfer to an external solver like a JMAG, of course, and achieve the final temperature distribution. That is the most important aspect we want to look at in this kind of system, of course, to guarantee a very long working life for our Emotor. But another aspect, as you can see here, or another possibility, is to simulate everything, also the solid temperature distribution inside Particleworks. This is possible. I want to mention it. It's not ideal because it doesn't offer the same amount of course, degree of complexity that one specific FEA solver offer. But it's important to mention that it's doable. So you work with only one simulation and you can start to see temperature distributions and have an idea of them. So here is just a short demo of the Particleworks interface, just to give you an overview. Sorry. So basically, what we have here is the control view viewport for the simulation we are setting up. On the left here, we have the input elements, the results, and so on. So the outline of our simulation. So basically, inside the outline, okay, I just want to point out that also the post-processing is there. So at the top. In this case, we are looking at one specific simulation. As you can see, we imported different elements, STL elements from the CAD, separated by means of course, the kinematic laws that we have to apply. So we want to separate every element that has a particular kinematic law or a different boundary condition in terms of temperature. Then we have several inflows at the top, jets going directly on the windings. We can hide the specific elements and or activate them for the physics. And then in the result folder, we have the particles generated by the inflows that we can visualize directly in Particleworks. While the simulation is running also, we can visualize in the same viewport of the simulation setup. We have in the view folder also the possibility to apply snapshots, so saved visualization. As you can see here, I applied a visualization, sorry again about that, a visualization where I have a map already done of the HTC coefficient a transfer coefficient on the windings. And this map was achieved and obtained in Particleworks with that post-processing methodology. So maybe discussing a little bit in detail that the mapping procedure allows us to select a specific model, STL, for instance, the windings in this case, and perform a projection of the fluid properties on that STL. We can average and obtain a CSV file as an output. We can take, in this way, an average HTC on the windings in the period that was considered. Okay, and at the end, you get something like this. You get a CSV file in the, if you open the directory, you can see that you have the CSV file inside it with all the information about the HTC values. So after that, we are basically at the end of this workflow, because we were able to extract the HTC for every surface. So we needed to transfer the CSV file to JMAG that was already prepared with the Emotor yaw losses analysis. And in this way, at the end, we can perform the thermal analysis and obtain the temperature distributions. So to transfer the CSV from Particleworks to JMAG, we have a specifically designed coupling tool that is shown here. What it will do is actually just to parse and select for the necessary columns in the CSV file generated from the mapping. And in this way, then you can import it in JMAG. What about the validation of this methodology? We did a very interesting comparison of the simulation results we were obtaining with this methodology together with Riccardo. So their objective was to measure a max difference between the simulated results and the experimental results of 5 degrees. What we showed for the windings area is actually that we are in the range between simulation and experimental results in a range of 2.8 degrees Celsius. So almost half of the requirement, the maximum requirement for the applicability of the methodology required by Riccardo. So after that, after this validation, we also worked with other customers and we further validated the methodology. And yeah, right now we are very confident with the solution and with the settings. So yeah, it's increasingly interesting to see results and approaches in this field. Moving on to the transmission side, as I mentioned, the e-drive is also usually coupled with the e-motor. And let's have a clearer view then to what is the observation that we can extract, what is the output that we can expect from Particleworks in simulating transmissions. So as I mentioned, this is actually the first field of application of the software. So we have even greater experience in this regard, and more and more customer using it for this kind of approach. So really coupling the two is very suitable and interesting. So what our customer usually do is to analyze the lubrication methodology in this kind of system, comparing oil splashing with forced lubrication. We usually see the methodology applied for different RPM or oil level, different geometries, or also to analyze how an integration of a new geometrical element can impact and influence the flow distribution and the lubrication levels. And also one other aspect that is investigated is extreme conditions. So ill starts or panic stops, or let's say situation where we have big acceleration applied to the system that can change the oil distribution quite significantly. So one of the first application or validation in this regard was done with Comer Industries, this company that develops coupling gearbox together with other things like axle and so on. In this case, focused on the coupling gearbox between an electric motor and the axle. So this is the system that we will discuss in detail. And the requirement was to simulate and provide a virtual prototype of this system that was able to provide some answers in terms of design in a matter of 1 week. Previously, let's say CFD tools could not guarantee results in 1 week. Actually, the previous methodology with a lot of work required at least 1 month. But with this methodology, we were able to simulate several conditions in, again, less than 1 week. And in this way, we could compare for, again, different loads and also rotating directions. We could compare the lubrication levels for bearings, the bearings on top as well, especially because they were the most critical. And we could compare those lubrication level with a real-life prototype. As you can see here, we are looking at the same conditions simulated and measured experimentally. We can see clearly the oil film created on the bearing, central bearing. We can see that there is much less oil on top. And yeah, here a clearer view of the film that can form there. And of course, the advantages of using simulation instead of clear casing is that first, you can create with significantly lower costs a virtual prototype. You can get information that you don't have access to with the clear case because you cannot inspect internally, for instance, and you cannot extract very accurate oil measurements, or not easily at least. So the idea is that with this methodology, we can provide fast design solution to improve the design without having to create the prototype and testing it. So in more detail, what was done here was for every load case was to compare the lubrication level as observed by the simulation and also the clear case. And we could see that there was a good correlation of the bearings lubrication levels. As shown here, we had 4 degrees of lubrication assigned to the different bearings, B1, B2, B3, and B4. And we could see very strong correlations between the simulation and experimental results. We, of course, don't have only oil bath lubrication system, but we can also analyze direct jets on the gears for more critical applications. In this case, for instance, we can analyze the oil distribution on the teeth of the gear. We can, in this way, reduce the temperature of the gear, and also run in general. We want to run with less oil amount so that we reduce the churning losses. In the analysis of, let's say, direct lubrication, we can also map and understand what is the covered area, and we can vary the jet properties accordingly. And another aspect that I mentioned is oil sump scavenge analysis. So in a lot of systems, we have a circuit that redirects oil from the sump of from the filling oil to the injection areas. But of course, we have to guarantee that the sump is always able to extract oil from the baffle at the bottom. So what we see here, we can clearly see the effect of accelerations on the oil distribution, and on the right we can monitor for different accelerations what is the effect on the flow rate at the pump. So in this way we can study our system, we can understand if we can provide lubrication for every acceleration, and we could also think about let's say covers or ways to always allow the pump to work efficiently. It's important also to mention that Particleworks now is completely integrated in Romacs technology. Some of you might be familiar with this software that is a gear box and gear designer tool. So what we can actually do inside Romacs is now to directly transfer and then implement from the same CAD a CFD simulation. So it's very easy to transfer this kind of model that is used for, let's say gear design and also stresses analysis. It's very easy to transfer this geometry to a simulation, and to a simulation that is able to give us in this loop information about churning losses, lubrication levels, and cooling efficiency. So we can really speed up also in this way the design, not only considering the deformations or the stresses on the gears, but also the effect of these choices on churning losses and lubrication analysis. So in general, what we want to do in this case, but also in the Emotor case, is to have a virtual prototype that is right at the first time, at the first design. So again, the coupling with the Romacs further expand our capability to speed up the simulation process and to integrate it in the design phase. And what we were able to conclude from these experiences and the feedbacks from our customer is that, the use of simulation and the CFD, thanks to Particleworks, is very well integrated in the R&D workflow, is able to provide in significantly less time as we were using in the past. It's able to provide information about improvements and of the cooling system, but also the lubrication of this kind of system. And in this way, we can reduce the time to develop, we can reduce the risks, the costs, while of course providing additional know-how and increasing the performances. So for now, I think I'm finished with the presentation, and I'm available for more questions if you to answer your questions.
Yeah. So thank you, Michele. Thank you for this great presentation about Particleworks. So feel free to tap into the chat box of Zooms or Wova any question that you have about this presentation. So I have one question, Michele. So is it possible to analyze the effect of the jet velocity and position of the jet nozzle?
Yeah, of course. In the improvements, here of the Emotor and system cooling, we have different strategies. One is to, of course, understand the flow distribution between the different nozzles. One other aspect, it's not included in this model, but we could have flanges or additional geometrical elements that can control the position of the jet at the exit here. So if you think about having a nozzle here or redistributing with significantly longer channel the oil, we could really optimize also the impinging area and the spraying of oil on the winding. So that's yeah, an advanced topic we can take a look at, but yeah, for sure that's possible and that's done.
Thank you. So, and the next question is, how long does it take to run electric motor simulation?
Yeah, so that's a good question, actually. It depends on quite some factors, like the amount of oil that we need to simulate and that accumulates inside the Emotor, the flow rates, the RPM, of course, because the simulation time step is also connected with that. But in general, and also the hardware, Particleworks allows for multi-GPU computation. So depending on the hardware strategy that you use, you could have also reduction of 2 to 5 times. But in general, let's say we are in a range of 1 week, something like that, for the entire simulation process. But again, there are several factors that could make it feasible in less time or make it longer, like max 2 weeks.
The last question that I have, how much does this cost, the Particleworks software?
So yeah, the licensing, I mean, I don't have a pricing to share here, but yeah, if you want some additional information, I would suggest you to contact us, so we can give you yeah, information about both the licensing, because it also in this case it really depends on your request, how many users you want, if you want yeah, a longer or a shorter license and so on. So please contact us. Let's say the order of magnitude is similar to other CFD solvers.
Okay, thank you.
Yeah.
Okay, so thank you for your answer, Mr. Michele. Just to add some information about the next presentation. So he will start on 5 minutes, something like that. And it's about a better way to design and test motor drive. So it will be presented by Mr. Peter Garnett. So feel free to use the feel free to go to your VUA and to go to the link of this presentation to join the presentation. Okay, so thank you, Michele, for this presentation, and thank you for all the attendees to join this presentation, and you will see soon.
Thank you all. Have a nice one.
Bye.